So this video corresponds to the guided notes that we have on electrolytic cells. On my Canvas page, I've linked to a video by Tyler DeWitt that explains electrolytic cells, but I want to stress a couple things. Right? So first of all, electrolytic cells, when you see the diagrams, can look a whole lot like voltaic cells, but there's some key differences. All right. So again, voltaic cells we went over in the last video. So the key thing difference between a voltaic cell and an electrolytic cell is in a voltaic cell, you're taking a process, a chemical reaction that naturally wants to occur, or in other words, a spontaneous chemical reaction, and using the energy from that to create electricity. All right. In an electrolytic cell, what we're going to do is we're going to do the opposite. We're going to take electricity and we're going to use that to cause a non-spontaneous chemical reaction to occur. All right. So you can, as a little bit of an analogy for the difference between these two, I'm just going to make the, first of all, talk about a dam. All right. So the way a dam works is that you use something that naturally wants to occur. All right. So let's say that we build a big dam, and this would be like looking at it from sideways view, where you've got high water over here, and you've got this big wall, and then we get a little break in the wall, and we let water go through. All right. So one thing that we know happens is high water naturally wants to flow downhill. All right. And there's a type of energy involved in that. It would be gravitational potential energy. And we can use that natural tendency of water to want to flow downhill, and we can use that to drive a generator, which would then create electricity. All right, so you're taking a naturally occurring process, and we're using that to create energy or electricity. All right, and that's the way this type of voltaic cell would work, or any type of voltaic cell. You're taking a chemical reaction. In this case, it's the zinc wanting to give its electrons to copper ions. That's a natural process, and you're using that to create electricity. All right. But in contrast to that, well, could we take something which was naturally did not want to happen and use electricity to cause it to happen? All right. So one thing that doesn't naturally want to happen is lower water going towards higher water. All right. So like if we just had this hole in the wall, we know that water would want to go this way from high to low. All right. But if we installed a pump in that hole, could we use electrical energy to force water to do the opposite, to go from low to high? All right. And with a pump, if you put energy into the system, you could cause that to happen. And that's the way electrolytic cells work. All right, we're going to go through. I'll sum up the basic fundamental principles of it here, but essentially that's the whole purpose of it. You're taking that chemical reaction that does not want to occur, and you're forcing it to occur by the addition of some electrical energy. All right. So, okay. So first of all, we mentioned that it takes a process that doesn't naturally want to occur and causes it to occur. So I want to step back and mention a little bit about this, a type of thing that we're going to be doing. We're going to, first of all, sodium metal. Sodium as a pure metal is something that doesn't naturally like to occur in the natural environment. All right. All the sodium metal that has ever occurred has been made through an artificial process or a man-made process. All right. And the reason for that goes back to something that we learned a long time ago, which is called the octet rule. All right. Let's say that we were to have pure neutral sodium metal. All right. If you remember electron configurations, this would be the electron configuration for sodium metal. And you say, all right, well, we know that atoms like to have full outer layers. All right, so if we take a look at this configuration, it looks like we have this one electron in the third layer, and that's going to make this not so happy. It's not going to be a stable atom. Sodium metal would like to get rid of that outer electron so that it would then have a full outer shell. And that's why it likes to exist as sodium ion. All right. So I've linked a video on my Canvas page that shows actually what would happen if you do have pure sodium metal. If any sodium metal were to exist in the Earth's crust, as soon as it hits some water, it would want to give its electron to that water, and this process right here would occur. All right, it's actually a pretty violent reaction. But when watching that video, you can kind of understand why we don't have any sodium metal in the Earth's crust. All right, so let's talk about a process, a chemical reaction that would naturally want to occur. All right, so if you were to take sodium metal and combine it with some chlorine gas, all right, what would happen? All right, so would it be the sodium and chlorine want to make sodium chloride, or does sodium chloride naturally want to break apart and make these two things? All right, well, we can talk about this in terms of the octet rule again. All right, so again, we talked about the fact that sodium would rather be sodium metal because this is the form of sodium that has the full outer shell. But if we drew a, well, this shows it as a Lewis dot diagram, and this shows it the neutral chlorine atom with its electron configuration. Well, does this have a full outer shell? Well, no, it needs that one last p electron in order to have that full outer shell. So a neutral chlorine atom would rather gain an electron to become chloride ion. All right, so that's stable right here. Well, that's why if you take neutral sodium and you have chlorine gas, which is a source of neutral chlorine. It's actually two of these guys which are covalently bound to each other, sharing that single electron, making the covalent bond. If you react these two together, the electrons from the sodium are going to be given to the chlorine. All right, so the sodium would end up being oxidized because that's 0 going to a +1 charge, and the chlorine would be being reduced because that's 0 charge or 0 oxidation number going to a -1 oxidation number. All right, so that's the natural process that wants to occur. So the obvious question is, how would we ever be able to have pure chlorine gas? All right, and how would we ever be able to have pure sodium metal? All right, the answer to that comes from this process of electrolysis, or the use of electrolytic cells. Okay, so I've linked to a video on my Canvas page that explains the process. It's another Tyler DeWitt video, and it does a very good job of explaining the process. But I've drawn a little diagram here that sums up most of the important principles. All right, so in the electrolytic cell, all right, let's what you're going to have first of all is you're only going to have one vessel. All right, recall that in the voltaic cell you actually had two separate vessels, and there's a reason that you had to have those separate. But that concept does not apply in the electrolytic cell. So what you're going to have is molten sodium chloride. All right, so in this area right in here, you're going to have a bunch of Na pluses, and Cl minuses. All right, and they would be all mixed together. All right, so one thing to point out is why does it have to be melted sodium chloride? Well, the reason it's got to be melted sodium chloride is if you took a look at the structure of solid sodium chloride exists in what we call a lattice, crystal lattice arrangement, where you have this alternating pattern of positively charged sodium ions, or the purple ones would be the positive sodium ions, and the negatively charged chloride ions, and these are all kind of locked in place. All right, and in order for this process right here to occur, those ions have to be able to travel to either one electrode or the other. And if it's in its solid form, they're not free to move around. So, but if we melt it, it would be like all of these purple and blue balls have the ability to all slide past each other because it would be liquid. And that's what happens when you have a liquid. The particles are free to move around each other. All right, so you've got the molten sodium chloride, and even though it's molten, your chlorides would still be Cl minuses and your sodiums would be Na plus, and they would be totally happy to stay that way. All right, sodium doesn't want to become Na sodium metal. All right, that's the opposite of the direction it wants to go. That takes it from being a stable atom and forces it to become more unstable. All right, so how are we going to make this happen? All right, we're going to force an electron on it. All right, in the same way sodium is stable, or sodium ion is stable, Cl minus is stable. All right, it doesn't want to give up an electron, and we're going to force it to give up an electron with some electrical energy. So again, we're going to force this process to happen through the introduction of a battery. All right. So in this battery, the positive end of the battery is going to act to pull electrons away from this electrode right here. And the negative end of the battery is going to supply electrons or push electrons towards this electrode right here. All right. So if we push electrons this way, basically there's electrons that essentially want to come out of this electron. And if there's something there that is capable of accepting those electrons, that thing could get reduced. All right. And that's what's going to happen. Since the electrons are getting pushed that way, this is going to become slightly negatively charged. That's going to attract the Na plus ions that are in the molten sodium chloride, and it's going to then provide an electron to that sodium. And when that happens, that then becomes neutral sodium atoms. And so all these neutral metal sodium atoms are going to start to accumulate on the surface of that electrode right there. All right, and so you might wonder, well, if the sodium atoms start to coat this this electrode, would that somehow inhibit the process? All right, well, the thing about it is, sodium metal, since it's a metal, is itself a conductor. All right, and so even if you start to accumulate some sodium on the outside of this electrode, well, metals conduct electricity. The newly formed sodium would then be able to carry electrons that could then be donated to the additional sodium plus ions out here. So the fact that this thing gets coated doesn't prevent this electrode from doing what it wants to do. All right. So on the other side here, we've got chloride ions, which are going to be attracted to this slightly positively charged electrode. And the reason it's slightly positively charged is it's got electrons that want to get pulled from it. All right. And once the chloride ions are near this electrode is capable of accepting electrons from the chlorine. And if that happens to two of these guys, all right, well, if you've got two neighboring newly formed neutral chlorine atoms, they can form a molecule of Cl2. All right. And that's what we mentioned about right here. The newly formed Cl2 molecule, well, Cl2 is a gas, and it's going to want to bubble away from that. All right. So since this is molten sodium chloride, it would be able to bubble away because it's within a liquid. All right. So I just want to sum up the process that makes this occur. What is it that it causes the pull of electrons and the push of electrons that we have here? All right. And that's done with a battery, such as this one right here. And I'm going to turn it around actually this way. And if you've ever looked at a Duracell battery, one thing you'll notice about it, like if you look at the positive side right there, all right, that would correspond to the positive side right here. And if you notice, the thing about the Duracell battery is it's actually colored copper on this end. Their trademark is the copper top battery, and that's not a coincidence, because literally what's happening on the positive end is that's going to be the side where copper ions accept electrons and become copper zero. All right, that's the process which requires electrons. All right, and when you pump, that's why there's a force that pulls electrons that way. And on the other side, you've got the zinc that wants to supply electrons this way. All right.